A warm greetings to everyone present. My name is Jovita Biju and today I will be presenting our research on predicting water quality and potability using hybrid machine learning models. Access to clean and safe drinking water is a fundamental human right. Contaminated water can lead to serious health issues including gastrointestinal infections, reproductive problems, and neurological disorders. Therefore, monitoring and ensuring water quality is paramount to protecting public health. In this study, we explore the application of hybrid machine learning models to predict water potability. Hybrid machine learning models combine the strengths of various algorithms to enhance predictive accuracy and reliability. By leveraging these advanced techniques, we aim to provide more accurate and efficient water quality assessments. This presentation will review current methodologies used in water quality monitoring and highlight the potential of machine learning to revolutionize this field. Traditional methods, while effective to some extent, often fall short in terms of speed, accuracy, and adaptability to diverse conditions. Machine learning offers a promising alternative by analyzing complex datasets more effectively and providing quicker, more precise predictions. Our main goal is to explore hybrid machine learning models for predicting water potability. First, we aim to evaluate the performance of hybrid models against traditional machine learning models. This involves a thorough assessment of how these hybrid models stack up in terms of classification, accuracy, and robustness. We hypothesize that hybrid models will demonstrate superior performance, offering more reliable predictions of water potability. Now let's delve into the key definitions and parameters that underpin our study. Water quality refers to the various characteristics of water, including its chemical, physical, and biological attributes. Potability. This is a measure of how suitable water is for human consumption. There are different parameters used for assessing water quality. Under chemical parameters, we consider factors like pH, hardness, total dissolved solids, the concentration of chloramines and sulfate, electrical conductivity, organic carbon content, and trihalomethanes concentration. There are also physical parameters like turbidity and temperature, and biological parameters like microbial contamination and presence of pathogens. By thoroughly evaluating these parameters, we can gain a comprehensive understanding of water quality and determine its potability, ensuring it meets the standards required for safe human consumption. Now let's walk through the methodology we used in our study. First, we have data preprocessing. Once we collected the dataset, we applied various preprocessing techniques to clean and prepare the data for analysis. Next, we conducted exploratory data analysis. This step involved examining the dataset to understand its structure, distribution, and key characteristics. After EDA, we moved on to model training and hyperparameter tuning. We split the dataset into training and testing sets and then trained various machine learning models, including our proposed hybrid model. Finally, we performed model evaluation. We assessed the performance of our trained models using metrics such as accuracy, precision, recall, and F1 score. In this slide, we will discuss the features of the dataset used in our study. Each feature represents a different water quality parameter that contributes to assessing water potability. First, we have pH, which indicates the acidic or alkaline condition of water. It's a crucial parameter because extreme pH levels can be harmful to health and affect the efficiency of water treatment processes. Next is hardness, which refers to the capacity of water to precipitate soap. Solids measure the total dissolved solids in ppm. High levels of TDS can affect the taste and safety of drinking water. Chloramines are used in water treatment as a disinfectant and their concentration needs to be monitored to ensure safe drinking water. Sulfate measures the amount of sulfates dissolved in water. High sulfate levels can cause a laxative effect and affect the taste of water. Conductivity is the electrical conductivity of water. It provides an indication of the amount of dissolved salts and other chemicals in water. Organic carbon measures the amount of organic compounds in water. Trihalomethanes represent a group of chemicals formed as a byproduct of water disinfection. These compounds can be harmful in high concentrations. Turbidity measures the light emitting property of water. High turbidity can indicate the presence of suspended particles which may harbor harmful microorganisms. Finally, potability indicates if the water is safe for human consumption. This is the target variable in our study, classifying water as either potable or non-potable. By analyzing these features, we aim to build a robust model that can accurately predict the potability of water samples. Next, we will discuss the crucial steps we took in data preprocessing. First, let's talk about handling missing values. In our dataset, some columns had missing values which could adversely affect our model's performance if left unaddressed. We used two primary techniques, imputation and removal. Imputation involves replacing missing values with meaningful estimates, such as the mean or the median of the column. This technique helps maintain the integrity of the dataset. In contrast, we removed rows where essential features had missing values that couldn't be reliably imputed. Addressing missing values is vital to ensure our model is trained on complete and accurate data. Next, we address outliers. Outliers are data points that deviate significantly from the rest of the dataset. They can skew statistical analysis and affect model predictions. We used various detection methods such as box plots, heat maps, and histograms to identify these outliers. Once detected, we decided whether to remove them or return them based on their impact on the model. Lastly, we perform normalization and scaling of the data. This step is essential to ensure uniform feature scales, especially for the distance-based algorithms and models sensitive to feature magnitudes. We used standardization techniques to bring all features to a similar scale. Normalization and scaling help improve the convergence and performance of many machine learning algorithms. Next, an exploratory data analysis was conducted on our preprocessed dataset. This step is crucial for understanding the underlying patterns and distributions in the data, which informs our subsequent modeling approach. First, we performed histogram analysis to visualize the frequency distribution of various water quality parameters. This step helps us understand how values are spread across different features. Our observations indicated that pH and trihalomethanes exhibit a normal distribution, while sulfate shows a left skew distribution. Next, we examined the pairwise relationships between features using a correlation graph. This graph highlights the strength and direction of linear relationships between variables. Understanding these relationships helps us identify which features are most strongly correlated, guiding feature selection and model development. From the correlation graph, we observed that most features have little correlation with each other except for pH and hardness. Identifying and handling outliers is a critical step in EDA. We used box plot analysis to detect outliers. This visual method provides a summary of the distribution of different water quality parameters and helps in identify potential outliers. Our key finding was that the solid feature values deviate significantly from the rest of the dataset. Addressing these outliers ensures that they don't skew our statistical analysis and model predictions. We also conducted hypothesis testing to compare the means of features between potable and non-potable water samples. Using a t-test, we assessed the significance of differences in feature distributions. The results indicated significant differences in the solids and organic carbon features between potable and non-potable water. Finally, we visualized the class distribution of our dataset using a pie chart. The pie chart revealed about 61% of the water samples are non-potable while the rest are potable. Next, we will discuss the proposed hybrid machine learning model for predicting water potability. Our hybrid model consists of two primary components, random forest classifier and deep neural networks. The process begins with training a random forest model. After training, we extract features generated by the random forest and use these as input for the neural network. This two-step approach leverages the strengths of both algorithms. Now let's look into the architecture of the deep neural network used in our hybrid model. The neural network comprises 5 layers. The input layer consists of 64 neurons. Each of these neurons connects to 9 features, resulting in a total of 576 connections. The network learns optimal weights during training to make accurate predictions. The final layer is a dense layer with a sigmoid activation function which is suitable for binary classification tasks. The advantages of using this hybrid model are as follows. By integrating random forest and deep neural network, the model leverages the unique strengths of both algorithms. Random forests are excellent for feature extraction and handling imbalanced data, while neural networks excel at capturing complex patterns and relationships in the data. The combination of these models helps mitigate overfitting, a common issue in machine learning, especially with neural networks. The hybrid model demonstrates superior predictive performance compared to traditional machine learning models, and the model is highly adaptable to diverse datasets. By combining both the models, our proposed hybrid model aims to achieve high accuracy, robustness, and adaptability in predicting water potability. This slide shows the training setup we used in our study. We split the data into training and testing set, where the testing set is 30% of the data. We used Adam Optimizer and trained the model for 100 epochs. We used binary cross entropy as our loss function. Now let's look into our results. The table provides a comparison of accuracy, precision, recall, and F1 score of various machine learning models. The best performing model is the hybrid model with 68% accuracy. Accuracy of traditional models range between 59% to 64%, and the worst performing model is KNN with 59% accuracy. These are the validation metrics used to assess our model. A precision of 67%, a recall of 62%, and F1 score of 62% were observed, which were the highest among all the models used. Now, I will move on to the conclusion by listing the benefits of our model, challenges faced, and the possible future directions. Let's start with the benefits. By integrating diverse data sources and leveraging multiple algorithms, the model allows us to monitor health trends more accurately and respond swiftly to emerging public health issues. Furthermore, the model combines various algorithms, each with its strength, to provide more reliable predictions. Now let's address the challenges we have encountered. Firstly, data availability remains a critical challenge. Access to comprehensive and high quality data is essential for the model's effectiveness and generalizability across different scenarios. Secondly, as our model becomes more complex with the integration of multiple algorithms, ensuring its interpretability becomes increasingly important. Lastly, scalability is another area of concern. As the volume and complexity of data grow, maintaining the model's performance and efficiency poses scalability challenges that we are actively addressing. Now, looking forward to the future directions. Firstly, standardizing protocols for data collection and processing will improve consistency and facilitate comparisons across different datasets and regions. Secondly, enhancing data sharing initiatives among stakeholders will promote transparency and collaboration, ultimately enriching our model's capabilities and reliability. Lastly, fostering collaboration with academia, industry, and governmental organizations will enable us to leverage collective expertise and resources, driving innovation and advancing public health analytics. In conclusion, our hybrid model represents a significant step forward in leveraging data and technology to improve public health outcomes. With a clear focus on addressing challenges and pursuing collaborative opportunities, we are committed to advancing the field and making a lasting impact. Lastly, I would like to acknowledge the support and contributions of Dr. Alvin Poulose, Assistant Professor at ISA Thiruvananthapuram, and Chetan Badgujar, Assistant Professor at University of Tennessee. And I thank the organizers of ICUFN 2024 for this great opportunity and all the listeners for your valuable time. Thank you.